The size of the equilibrium constant can actually give a lot of information about the reaction itself. So we have three categories that we stuff K into: a small k, a medium K, and a large K. So a small k is going to be less than 10 to the negative third. A medium K is going to be 10 to the negative third to 10 to the positive third, and a large K is going to be greater than 10 to the positive third. And so when we're dealing with an equilibrium constant, we first want to look at the size of K. And from that, we can start to make judgments about the overall reaction. So let's take a look at what happens with each of these Ks and some math tricks we can use to make our life easier. Because up till now, we've been really lucky. Our math has worked out just fine, that we haven't had to do anything messy. But sometimes things don't work out so pretty, and you end up having to do things like solve a quadratic. It happens. All right, but with certain understandings about the size of K, sometimes there's math tricks we can use to get away with not having to solve a quadratic. All right, let's take a look. So when I look at the size of K, okay, and I have a small k, so that's that k that's under 10 to the negative third, the reaction hardly proceeds at all, which means that the reactants predominate. Okay, not much product is formed. Okay, now if I've got that intermediate K, I have an appreciable mixture of both reactants and products at equilibrium. And then when my K is large, essentially the reaction proceeds to completion. Not a whole lot of the reactant is left and the products predominate. Okay. Now, realistically, a lot of the systems that we deal with, that small k is going to be the one that you're going to see most often. But it's not the only thing you can encounter. So let's take a look at each of these. So here I have a reaction system. So I say that this particular equilibrium has a large K. All right, so I get K is equal to this hydrogen bromide raised to the second power over the hydrogen and the bromine. And this is large. So it's going to be greater than 10 to the positive third. Okay, so when I look at this, my reactant particles are the white and the brown, and then my product particles are the white and brown hooked together. So this is a snapshot of the system at equilibrium. Okay, so I have one bromine and one hydrogen, and 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogen bromides. So at equilibrium, what do I have most of? Reactants or products? I have products, all right? So products predominate. Okay, little to no reactant is left. All right, so conversely, I have this situation. I have a small k. So my k here, I've got nitrogen monoxide raised to the second power, nitrogen, and oxygen. So this is similar to the previous reaction where my product was raised to the second power and my two reactants each had no coefficient, all right? So this is small, and so this will be less than 10 to the negative third. All right, so this is, again, at equilibrium. So when I look at this, okay, the blue and red hooked together are my products, and I only have two of those products at equilibrium. I have a whole lot of those reactants. And so when K is small, the reactants predominate. And depending on how small that K is, not a whole lot of product gets formed, and it's mostly just left intact reactant. Okay? All right, so here I have some pictures for you. So In the first picture, we go from orange to that kind of greenish yellowish color. All right, so my orange is my reactant, and that greenish yellowish color is my product. So in the box is what happens at equilibrium, or is what occurs, or the system at equilibrium. So in our first box, what would you predict for the size of the K? Well, there's not a whole lot of reactant left, is there? So this should be a large K. All right, greater than 10 to the third. Hey, what about that middle box? What do you think that one is? Well, we've got an awful lot of those blue balls left and only one red ball. So not a whole lot of product was formed. So this is a small K. And again, this is less than 10 to the negative third. All right, and then that last box, I've got pretty equal mix of both of those colors left at equilibrium, right? So what would this be? This would be that intermediate or medium K. And so that's at 10 to the negative third to 10 to the positive third. 10 to the positive third. Okay. And you know, if it's closer to the 10 to the negative third, my equilibrium mixture will have a little more reactant. If it's closer to 10 to the positive third, my equilibrium mixture will have a little more product. Okay? So what this tells us is that the size of K can lead to some very important assumptions. All right? The most common, again, is going to be very small K. Okay, most common. All right, most common is small K. Again, up till now, we've been super lucky with our math. We haven't had to do anything crazy like solve a quadratic. So let's look at an example here. Let's say I had some carbon monoxide gas and some water vapor, giving me carbon dioxide gas and some hydrogen gas. And this reaction is a K of 1.56. So right there in the middle. So neither small nor large, all right? So we can't make any assumptions here. So our K expression here has carbon dioxide, hydrogen gas, carbon monoxide, and our water vapor. Now let's say you were given all your amounts and you did your ice table. And at the end of your ice table, you're left with this. Your carbon monoxide is 2 minus X. Your water is 1 minus X. Your carbon dioxide is X. And your hydrogen is also X. So if I plug this in to my equilibrium constant expression, I would get 1.56 is equal to X times X over 2 minus X times 1 minus X. Okay, I would end up getting 1.5x is equal to X squared over X squared minus 3X plus 2. All right, well, the math is starting to get a little bit grosser here, right? I don't really want to solve a quadratic, but I would do it if I had to, okay? Take you back to algebra days, all right? So to solve, we would need to use the quadratic. Okay? But what happens if X is small? Can we get away with not having to solve a quadratic if X is small? Well, let's see. So small k, remember, is less than 10 to the negative third. All right, so I've got some sort of system, A giving me B. Okay, so there's an assumption we're going to make. Assumption. X is very small. Okay, why are we making the assumption that X is very small? Well, remember, with a small k, what we're saying is that not a whole lot of product is formed, right? And so if not a whole lot of product is formed, that means I don't lose a whole lot of reactant. Okay, so X is very small. This assumption lets us discount X in the denominator. Now, what we're going to look at is we're going to take the initial concentration of A divided by the equilibrium constant, and what we're hoping for is this value is greater than 400. Okay, so to start off with, because here's the thing, when you've got an X, or when you've got a K that's borderline small, like say you do have something that's 10 to the negative third, the ability to neglect X in the denominator is really going to be dependent on what your starting concentrations are. When you get to smaller and smaller Ks, it's pretty much a given that it's going to work out, but it's a good idea to check. In fact, there was one time I was doing an example for, I think it was a Chem 142 class, a second semester general chemistry class, and we ran this check, and our answer came out to be something like 402. So it just barely passed the check in order to continue with the assumption. Okay, so what are we doing? We are assuming X is small and neglecting it in relation to the reactants. Okay, so we're making this assumption that assuming it's small and neglecting in relation to the reactants means that we're not going to have a very big error. Okay, neglecting it here in relation to the reactants, we're hoping for introducing an error less than 5%. Okay, because if K is small, very little reactant is lost, so it is considered negligible. Okay? All right, now, however, if that initial check of my concentration of my reactant over K is less than 400, then the assumption does not hold. The error would exceed 5%, so X could not be neglected, and you would need to solve a quadratic. Okay, so that's the assumption we're making. So we're going to do an example problem, and I'm going to tell you right now that the example problem I have has such a laughably small X, or in K, that it is obvious that it's going to pass the check. All right. Normally we're not going to deal with reactions that have such a laughably small K, but we will begin our exploration of this with a laughably small K. All right, so here is my reaction. I've got some oxygen gas converting to ozone. My K here is 1.1 times 10 to the negative 50th. Okay, so very, very small, right? We've got 0.211 atmospheres of oxygen. Calculate the final pressures of all species. All right, so we'll do our check. We're going to take our initial amount of the reactant over K and we're going to get 1.92 times 10 to the 49th. 1.92 times 10 to the 49th, absolutely 100% without a doubt, is greater than 400. All right, so we are okay with our assumption. All right, so let's take a look here. So we have our oxygen and our ozone. So 0.211 minus 3x plus 2x, 0.211 minus 3x, and 2x. All right, so we get K is our ozone raised to the second power over our oxygen raised to the third power. So we get 1.1 times 10 to the negative 50th is equal to 2x squared over 0.211 minus 3x quantity cubed. Okay, so this math would be disgusting, right? I don't want to solve that. Not only are I dealing with quadratics, but we've got like that cubed thing there, and I don't want to factor a three-pronged polynomial. Okay, so our assumption is that that x in the denominator dealing with the reactants is so small it doesn't even matter. So I'm going to make my assumption that that x falls out. It's just so little it doesn't matter at all. And so now what that gives me is it gives me this. I get 1.1 times 10 to the negative 50th. Dang, my Apple Pencil is all over the place today. So I'm still going to keep that 2x on the top, but now I'm going to get 0.211 cubed. Okay, so again, we're saying that that is just so small. We just lose so little reactant, it doesn't matter. And so it falls out of our denominator there. All right, which gives us 1.1 times 10 to the negative 50th is equal to 2x squared over 9.39 times 10 to the negative third. Okay, and then we do a bunch of algebra and we get x is equal to 5.08 times 10 to the negative 27th. Okay, and so my pressure of oxygen at equilibrium, if I take 0.211 minus 3 times 5.08 times 10 to the negative 27th, I just get 0.211 because that's so small. That doesn't matter, right? And then the pressure of my ozone at equilibrium would just be 2 times the 5.08 times 10 to the negative 27th. Super small. Now we can check. All right, let's do a check. Did we actually introduce less than a 5% error? Okay, so I'm going to take x over okay, I'm going to look at x, whatever I calculated x for, over my initial concentration times 100. So 5.08 times 10 to the negative 27th divided by 0.211 times 100 is equal to 2.4 times 10 to the negative 24th percent. All right, is that less than a 5% error? Yeah, absolutely. So it holds. And in fact, so this beast right here will solve for x for me, which is useful sometimes when I'm trying to do like quick stuff to prep for class. And so I actually ran that just using the equation solver just because I was curious, like what actually would it be? In this one, I wasn't surprised that it was going to be super close, but yeah, I got 5.08 times 10 to the negative 27th. No difference because it's just so small, okay? All right, now, What happens if the opposite case is true? What happens if I get a very large K, this 10 to the 6th? Okay, so the assumption here is the reaction goes to completion and all reactant is consumed. Okay, so how does this one look? So what we'll do is we've got our ammonia, our nitrogen, and our hydrogen. We've got our initial, we've got our change, we've got our equilibrium. So this we had a mixture of everything. So 2.7, 3.0, 4.6. We're going to completion, so we're going to lose reactant and gain product. So 2.7 minus 2x, 3 plus x, 4.6 plus 3x. We get something super insane, all right? We're going to get our equilibrium constant expression is the nitrogen, the hydrogen raised to the third power, and the ammonia raised to the second power. So we get 2.7 times 10 to the 6th is equal to 3 plus x times 4.6 plus 3x quantity cubed over 2.7 minus 2x squared. This is nuts. Again, I don't want to solve this. So our assumption is that it goes to completion. Okay, and because it goes to completion, all we care about is how much product is lost, right? Because it's just like when we solved ice tables for limiting reagent problems, right? We assumed we lost all of our product, and so we calculated x in relation to how much product was lost, and then plugged x in for our products, right? So that's what we're going to do here. We're going to say that this doesn't matter. We're going to say that this doesn't matter. And so we'll get something that looks like this. 2.7 times 10 to the 6th is equal to 3 times 4.6 over 2.7 minus 2x squared. When you do all the algebra, x equals 1.34. Okay? When I ran this mess on my crazy calculator up here, I got x is equal to 1.34. So it works. All right. So when you understand the magnitude of K, it's super, super useful, and you can do a lot of really cool math shortcuts. So a large K, you're just basically solving like we did for limiting reagent problems, where we only care about X in relation to the reactant. When X is really, or when K is really small, we're looking at X in relation to the products because not a whole lot of reactant is lost. And that's the most common one. K being small is the most common situation. Because again, when K is large, we just assume that the reaction goes to completion. And so we don't always necessarily care what K is at that point. We're just saying, well, I have this much starting material. How much product do I form? Okay. Now, this kit situation, successive approximation, this is something that some people like to use to get out of solving for the quadratic. So here I have a K of 1.11 times 10 to the negative second, which is an intermediate K. So we can't discount X in either the denominator or the numerator, okay? But, so you would have to solve the quadratic here. But what some people do is this thing called successive approximation, where you go ahead and you neglect X down in one spot. You solve, and then you plug X in, and then you solve, and then you plug X in, and you solve. So like you neglect X in the denominator, you get what X is, and then you plug X back into the denominator and solve it again. and get a new x, and then plug x back into the denominator and solve it again and get a new x. And you do this until they converge. You do this until the x that you plugged into the denominator equals the x that you solved by leaving it in the numerator, okay? It's just a brute force method instead of using the quadratic. This particular reaction, when I solved it using successive approximation, took me 7 iterations. I had to solve the equation 7 times, continually plugging the new x back in until it converged 7 times. I'd actually honestly rather solve the quadratic. To me, that is a more elegant method than this brute force successive approximation. So, but it works. It's just time consuming and it's not something that I enjoy doing. All right, so this is what we do if we have a very small k or a very large one. But again, mostly what we're dealing with in these situations is a small k. All right, size of k, it matters. It tells you about the reaction. I could ask you, hey, you have, a k of this size. What is your reaction for sir? Products, reactants, both. So important to know.